Welcome back to another exciting episode of Resenha COSMICA podcast, where we discuss about various aspects of universe, try to learn something about it. And today I'm really excited for this episode because for a couple of reasons. One is that I'll try to change the interactions a little bit, the format a little bit, make it more interactive, more engaging. Let's dive more into the guests and let try to know uh, more about him. And second thing is he's one of my close friends. That gives me more liberty to talk about various aspects. I've seen most of his growth in physics and outside. So, uh, and the third reason would be it's one of our own works. So we have more confidence in talking about our own work. So I'm very excited for this episode. So today's guest is, as I said, he's one of my close friends, Muzammil Mustaq. So we did our masters together in Heidelberg. In fact, Muzammil was the first person I met in the physics department when I first went to Heidelberg. Uh, and we have experienced academic ups and downs together. I remember struggling through GR course in our first semesters, and we have worked also part-time in various jobs. We worked together in the university clinic. Muzamil had a better job in the kitchen, whereas I was cleaning dishes. Uh, well, uh, and then Muzamil played a very important role in feeding me for a good number of days when I was almost homeless in Germany. And he makes, I have to tell you that he makes very good uh, various kinds of bhaji. But as I was vegetarian, but I'm sure he can make better biryani if I was eating biryani. But later on, we chose different, slightly different directions. I was more interested in theory. However, Muzamil was more interested in computational uh, astrophysics. So, but however, our institutes were very close. Uh, so Muzamil's Institute of Computational Astrophysics was in the foothills of Philosopher Weg, slightly in an elevated region. I was in ITP. So he continued to work with Ralph Klessen and Daniel Severino on FirstLight simulations. Ralph is one of the leading people you can think of in this area. Uh, and Daniel built this whole simulation FirstLight. So he was in good hands, and he he took up a very challenging task for his master thesis, and it was amazing work what he did. He ended up having two papers in the master's time, and so even though we were working on different aspects of the universe, we always had enthusiasm to discuss various other things. So we always spent time on discussing our own about physics, about the work, and what I really liked about Muzammil was he was really original in his approach to solving problems, which I have never seen anybody do it as he does. Like any problem you give him, he takes very original, very unique approach, uh, and that's what I really enjoy working with him. In fact, we even though we are very young in scientific career, Muzamil has been my longest collaborator, and we still continue to work. Uh, um, and I enjoy really working with him because what he brings to the table, the originality, he has a very unique problem solving skills. So Muzamil completed his masters from Heidelberg, and then he is now slightly deviated towards data science. He is doing another master's in, he's almost completing, I guess, his master's in data science in Kiel. And he'll be aiming for industry part, getting into industry. However, I'm sure his interest in learning more about universe will not stop. We are collaborating, and we will be collaborating in further more projects, studying different aspects of the universe. So welcome, Muzammil. How are you doing? All good?
Thank you, Prajwal, for the invitation in your podcast. I am very good. Thank you and hope you are fine.
Yeah, I'm doing good, man. So first of all, what I wanted to ask was, why did you include me in your projects? I want to start with this. Like, we have published, so during your master's work, you published two papers where which are like really amazing papers, especially with the current observations with JWST. We'll get into that, the technical aspects. But all I wanted to ask in the first question was, why am I involved in your works? Because if I remember, you did a lot of work for these things, and my input for your work was very insignificant, I would say.
Prajwal, in this case, I must say that you were my approval. If I was doing something, you approved that thing. So you were even beyond the teachers who guided me
Ah,
all the way through. Yeah.
well,
So that's why the purity all goes to you.
Well, I don't know. So much credit. I cannot take the so much credits, but I really appreciate. I'm really glad that we could collaborate on those two papers, and we are still working on several other exciting things, which maybe we'll do another podcast for those. So, starting with our works. So we'll be discussing a couple of papers which we published in 2022 and 2023, which were mostly dealing with the dust in early universe. When we say dust, it's cosmic dust, uh, and unlike our daily life dust, which we try to get rid of, cosmic dust is also insignificant in amounts in early universe. However, it plays a very important role in how star formation rates, and another important epoch, which was reionization. It has a very direct impact on how long the reionization epoch lasted, and various other aspects, from astrophysics to cosmology. So just to give an audience an initial setup to start from. So we have already discussed epoch of inflation in our previous podcast with Luis. Uh, so that's how we believe, at least, the universe started. After inflation, we had hot Big Bang epoch, where we have various kinds of particles production, and later on, we had first of all, we had dark matter decoupling from background cosmological plasma, what we had in the early universe. And this dark matter particles acted like seeds or potential wells into which the rest of the gas fell. And in these over densities, you have large molecular clouds, which were usually hydrogen clouds. And in these over densities, you could have star formation. But the point is, the universe was a dark place for a while. For the first 200 million years or so, for 200,000, no, 200 million years, the universe was a very dark place. There was no light until the first stars formed. Then we have UV, and this UV radiation was sufficient enough to ionize the neutral hydrogen we had in the intergalactic medium. And this was the very important epoch of reionization or ionization. Uh, so, uh, given this setup, where is the dust coming into the picture? Because everything was hydrogen. Uh, can you say, Muzammil, like how insignificant dust is in these early galaxies or early structures, as we know?
Hmm, Prajwal, my understanding is that yes, in the early phases of the universe, when the structures were forming and the galaxies were evolving, the amount of the dust was very low.
Hmm.
Yeah, it actually depends on the metallicity
Hmm.
and the proportion of the gas clouds within the galaxies. So the amount is actually like a exponent -5 or so.
Hmm.
This is like the density of the dust. So
Like just to give a picture, like usually, let's say a galaxy is of 10 to the power 10 solar masses, then the dust mass would be somewhat like a million solar mass.
exponents
Yeah.
exponent 6 or 7.
Yeah,
Yes.
so more or less a
Ye-
million solar masses. And
Yes.
most of the galaxy mass is mostly made up of either the stars and the gas mass.
Yes.
So
Yes.
dust is like really like 0.0001% of, no,
Exactly. That is true.
0.1% of
This
uh,
is true.
the
But Prajwal,
yeah.
we can also see that the dust, even with a very small amount, play a very important role,
Mhm.
especially in the formation and the evolution of the galaxies. Like why and how it is happening. Like dust is act as a black body
Yeah.
where it observe the radiations that is coming from the stars, and then it cool down it. Yeah.
Mhm.
So once the system, if you have the box, imagine you have the box where you have the dust particles, and the light that is coming going inside of it is getting cooler. So
Mhm.
once it gets cooler, the gas around it get a chance to become a more denser due
Mhm.
to the gravity
Mhm.
and forming. And this is the phenomena it starts for beginning the stars begin to form.
Yeah. So let's get into like what actually dust does. But before that, like just to give more idea, like I think we have to be clear on what dust exactly is. Like as you mentioned, it is something related to metal.
It
So
is
if you
a
can
yes.
define
It
what
is
dust is.
the components like the silicate or the graphite components, or even it could be anything which is not hydrogen.
Yeah.
Yeah.
So when we had the first stars, or what we call as protostars, which are usually like huge, massive stars. If you are very technical, you can call them like type O, B stars, population 3, what they call all this nomenclature. So these are very massive stars, dominant with hydrogen, and uh, since they are massive, they are also short-lived. They live for some millions of years, unlike our sun lives for like 10 billion years. So when they're short-lived, they die through a supernova, or there is solar winds. There is kind of feedback mechanism going on. What are the ways in which these early stars have these feedbacks to the stellar medium, or their medium? What are the kinds of feedback mechanisms we know of?
Okay, so first we need let's see what are the stars and how they produce its own light. Yeah.
Yeah, yeah,
So it is based on the nuclear fusion process.
yeah.
Yeah. When the two hydrogen elements get collapsed and
Mhm.
form a heavier element, which is the
Yeah,
helium.
yeah.
And this process depend on the mass of the stars, and the process will continue to grow until and unless the whole hydrogen is finished from the star. And then what happened, the star like the massive star as compared to our sun, it becomes it start contracting its own material,
Mhm.
yeah, to generate the energy. So there was a one point where it cannot further collapse, and the supernova and the phenomena like this happen. So
Mhm.
supernova is like we can say it a blast. It
Mhm.
released the immense energy.
Mhm.
So all the material that was inside the stars now become the part of the interstellar medium.
So this is how higher elements in the core of the sun gets outside or sun
Yes.
or any other star gets outside of a star and makes the environment richer in
Yes.
so that is what creates dust. So there are other processes like maybe stellar winds. There could be
But then we need to see that what proportion is the stellar winds, the solar winds, or these kind of things, the phenomena releasing the material from the stars to the space.
yeah.
So the ratio is very less as
Okay.
compared to when the star dies and
Okay.
it converted into the
So
supernova.
supernova is the major component in
We can say, we can
okay.
say.
Okay. So this is the thing with the proto stars, and also talking about the very first galaxies. So we have the proto stars, and then there is this mechanism going on, and we can call this region where there is new star formation, very irregular structure called, we can call it as a proto galaxy, right? So unlike our own galaxy, like beautiful Milky Way with arms, we didn't had any of those structures. So it was more of a very irregular bunch of star forming regions we can call as the first galaxies of that time. So now that you have a galaxy, a very individualistic galaxies, um, what do we do with these galaxies? Like what are the, so what are we studying with these galaxies you have? How they, so we want to talk how this light coming out of these stars in this galaxy impact the intergalactic medium, the region between galaxies. So because we still have neutral hydrogen everywhere in the universe other than the galaxy regions, so the light is the UV light, because they are, you have very massive stars, they emit UV radiation, and what impact it has on the intergalactic medium now.
So in the stage like the redshift of 7 or 6,
Yeah.
when the universe was like 400 million years old,
Mhm.
so the light from the stars were so strong that it start ionizing the hydrogen
Yeah.
outside the between the galaxies.
Yeah.
We call those region is the intergalactic medium. So this process was continued until the redshift of 6.
Yeah, it is still maybe debated, right? Like what, how long the reionization epoch lasted. But yeah, I think soon we'll get to know a very maybe slightly better understanding of how long this lasted. Um yeah, this is where I think the dust role plays a very important role in determining how long it lasted. So, um so what do we have now? So we have galaxies which are emitting UV, and this UV is being helpful in ionizing the neutral hydrogen we have in the intergalactic medium. So to give things in, to put things in perspective, let us put, I'll just put in because redshift may not be very um understandable terms for maybe public. So so the first stars may be formed after 180 million or 200 million years after Big Bang. Then we have redshift 6, which would correspond to I don't know how much years of universe.
I think 400 millions.
Okay, so the thing is, the time and time moves very non-linear in cosmology. So you cannot estimate, okay, this is how much years it passed. So well, so so the thing is, we are talking very early in the universe. So the redshifts, particularly which you studied, is from 6, 7, and 8, which is
Yes.
very important epochs. And today, JWST telescope has been seeing stars as close as like 10, even 13 or something. So it is reaching very initial stages of very first stars, we would say. So, well. Uh, so let's talk more about what are the effects of dust. So as you mentioned earlier, uh, dust acts like a UV absorber. There are two effects. One is it absorbs UV, and the other thing is it heats up and emits IR. So there are two of these things. Uh, what is attenuation? Can you explain, like, what is attenuation here?
So attenuation is actually the process. So the dust within the galaxy, it observed the the high frequencies light
Mhm.
coming from the stars. So it observed it. So the fraction it observed the light is, we call it the attenuation.
Yeah. So dust clouds or I mean the molecular clouds you have can absorb the UV light. Sometimes it
Yes.
may also scatter. It involves very complicated.
It is scattered, yes. The proportion of it get observed. Some of it is scattered and get observed by the other particles. So this is like the whole process. We can just say that dust particles as a black body. When a light ray go into the black body, part of it get observed and then scattered, and
Yeah.
it will going continue until all of the light ray get observed. However, the black body again re-emitted into the larger wavelengths,
Mhm.
longer wavelengths. So
Yeah.
the same procedure apply onto the dust particles,
Yeah.
because we initially consider the dust as in a local thermodynamic equilibrium.
Hmm. Yeah. And
So yeah.
go on, go on.
So if we just think about it, the dust and the light,
Yeah.
so the relation we can assume is that,
Yeah. Yeah. I think I can see the board. Yeah.
okay, so we can just say
Maybe
that,
slightly down. We cannot see. Yeah. Yeah. That would be good. Yeah.
okay. Prajwal, can you follow the equation?
So you have I equal to initial I naught and e to the power
Yes.
minus tau.
Yes. So this is actually the very foundational equation when we are talking about how the light ray passes through the medium.
Hmm.
So this is like a most fundamental equation for any kind of slab,
Yeah.
and how the light passes from the slab. So I know here is the initial light,
Hmm.
and the final light, the transmitted light is the I, capital I with the mu. Mu is the frequency.
Yeah.
So it depends totally on the frequency. So
Mhm.
this is the transmitted light.
Yeah.
And however, we can see it depends on the optical depth, which
Yeah.
is in the fraction of exponent minus optical depth.
Yeah.
So here the optical depth is showing, the optical depth is depend on the absorption coefficient,
Hmm.
then the density of the material, and how much, and the distance, that how much a light travel from a medium.
Hmm.
So here we can see that the initial light, if we just try to plot it, so how it look like, uh, possibly I not, and here is, we
Wavelength
can,
or yeah.
yeah, so this is actually the inverse relation. So here, I
Mm.
guess.
Mm. Yeah. Good. So now so this is with the um, also talking about the observation part, like the major, I think, problem studying early epochs is the fact that at least till recently we didn't had any observations or very less observations beyond say redshift 6. So all the observations we have is we look at the local galaxies, understand their properties well, and try to extrapolate it to, okay, maybe the same things were there in the early universe structures. But uh, and Hubble was one of the telescopes which actually probed a little further and gave us more data on further than Redshift 6. So, so is this the reason why people take the simulation approach to understanding aspects of early universe?
Prajwal, in this case, we need to try to understand what is the simulation and how it helps us. Yeah.
Mhm.
So the observation part and we have the theoretical part.
Mhm.
So theory give us the equation and the rules that how it's supposed to work.
Mhm.
But the authenticity always comes from the observations.
Yes.
However, the theory part is always far, far, far more future. How we are still and always lacking in the observational part. So simulations make a bridge between theory and the observations. So, for example, we were like a decade back, we were not able to observe the galaxies or the stars in the high redshifts.
Mhm.
So, what are the other alternatives? We were like trying to make some analogies. For example, how the dust behave, what are the characteristics of the dust, what is the initial properties of the dust. So in the local galaxy, in the local universe, we are seeing around that the Milky Way dust properties are different as compared to the SMC dust properties, because the Milky Way is having the more stars formation. Not sure I am, yeah.
Yeah.
So they are like a kind of more star formations or even more metals
Yeah.
in the Milky Way as
Yeah.
compared to the
Yeah. That is for
SMC.
sure. So Milky Way
In,
has more metal,
yes.
I mean, dust mass compared to, let's say, the early universe galaxies.
So, but in the SMC, the mass of the stars, the SMC mass is lesser. Same as with the metallicity. The metallicity
Yeah.
is way too less as
Yeah. Yeah.
compared to the Milky Way.
Yeah. This is
So
because
we
it is
consider,
a dwarf galaxy, right? It's a very small
yes,
galaxy. Yeah. Mhm.
yes. So we presume that in the high redshift, possibly the dust properties same as the SMC. So we implement the SMC properties into the high redshift for our simulations.
Yeah. Yeah.
So this is how we normally perform.
Yeah. So, what are the simulations? So you mentioned two things now. One, we discussed about the attenuation thing about the dust, how the intensity gets attenuated depending on the optical depth. And the other one, you just mentioned how people rely on simulations to get more insight of the galaxies. So, what are the kinds of simulations you had to work with for this work?
Yeah, it depends on the different types of project. For example, there are the simulations, we call it like a big box simulations and the small box simulations.
Yeah.
Big box is mainly used for the different purposes where you need a larger populations of the massive galaxies. However, the disadvantage with the small boxes is that the number of massive galaxies are very less as compared to the smaller galaxies.
Mm.
So for the but what is the advantage? So advantage is that it is very high resolutions.
Mhm.
So we can simulate it into the very small scales, and the radiative transfer simulations, it's supposed to be performed in a smaller scales.
Mm.
So where we assume the lesser and lesser presumptions and the accuracy will be higher. So the FirstLight simulation, first benefit is that it is a very high resolution simulation in a small box. The second benefit is the feedback process.
Mm.
In previous simulations, there were like not all the feedback processes possible, but the FirstLight simulations use the radiative as well as the supernova feedback effect.
Mm.
So it highly influence the results based on these two parameters. That's why we have decided to use the first light simulations to get our results.
Yeah, so you're talking about the FirstLight simulations, which is where you have a liberty to zoom in at some
Yes.
particular levels. Do you remember how much zoom in you can do? Up to some kiloparsecs, right? You can zoom.
Yeah, the kiloparsec, like at the radius of 25 kiloparsec, is actually a average halo radius
Yeah,
or
so
the galaxy radius,
yeah,
25 kiloparsecs.
yeah,
The smallest we can resolve is up to the 10 parsec.
10 parsecs.
Yes.
Whoa, whoa, whoa. So, so the point is, we have to understand that we cannot have entire simulation of the universe so far. Like we can only simulate every section of the universe. So, for example, we are talking about the early universe, so we can only have a certain redshifts, let's say. So, be making it that clear. So there is now you also so given that this n-body simulation, then you also use the Polaris, which is the which involves takes into account various kinds of radiative transfer mechanisms, and it computes spectral densities, I guess, right?
Yes.
So, so you make use of these two simulations to know better what were the radiative processes involved in the early universes and what were its consequences for
Yes.
the first few, I mean, in the early redshifts. Okay. So there are two wavelengths as we mentioned. One is UV,
Yeah.
which dust absorbs. Then there is IR, which
I.
dust emits. So we're talking about absorption UV. The thing is we compute the UV attenuation. So as you mentioned, the UV gets attenuated.
Yes.
So the famous model for this attenuation is something called, which you are familiar, like I mean, we have discussed a lot about this guy, Calzetti. So tell us about this Calzetti model. Like what is like how did this guy came up with this thing?
So in 1994, Kazeti observed about 40 different galaxies in the local universe and find the attenuation in those galaxies. So the model that he so the model he introduced matches very correctly into the high redshift galaxies as well.
Hmm.
The same as we have the different model as well, like the Milky Way model, the SMC model,
Yeah.
but all the models giving a different results.
Because
Like
they
if
are
we are saying
based
that,
on local universe, right?
yes, yes, and also depend on the intrinsic properties of the galaxy.
Yeah.
Like the attenuation curve, it is just the ratio of the attenuation uh, versus the wavelength.
Yeah.
So we can see that the attenuation
I think I can
can.
pull up our paper. I think
Okay.
it's the best time.
Okay.
So this is the paper we are talking about. Uh, and let us go to the dust attenuation part. So this is the plot you are talking about, right? So
Yes,
here you can
exactly.
see the SMC part and also the Calzetti in the green dashed lines.
Yes. So here we can see that the attenuation curve is actually the ratio of the attenuation at different wavelength
Yes,
uh, by the attenuation, especially at the visible light. So
yes.
we get a ratio, and so the advantage of this ratio is that it does not depend on the masses of the galaxies. Yeah.
Okay.
So we get the exact shape that how the curves of the attenuation varies.
Hmm.
So if we see that at the longer wavelength, we have a very high ratios, and we compared it with the two different models. One is the SMC and the causality.
Yeah.
Both are the observational. Causality, as we have mentioned, it is the observations of 40 different local galaxies
Yeah.
observations.
Yeah.
So here, what the main thing or the key points we can say, first is that the attenuation curve is varying based on the masses of the galaxies.
Mm.
The lower the mass, having the higher attenuation curve,
Yeah.
and then the slope of the curve is decreasing
Yeah.
when the mass of the galaxies, the stellar mass of the galaxies increase.
Yeah.
So we have noticed in the recent years, the scholars from the Italy and Japan,
Hmm.
they have published the results of the James Webb Space Telescope,
Yeah.
where they have mentioned they observed the galaxies at the redshift of 8.
Mm.
So those galaxies range were lying between the 2.5 to 3.5,
Mm.
which exactly matches uh, where it exactly matches with our curve
Yeah.
high stellar mass
Yeah. So
galaxy.
you're talking about the slope, right? Slope is
Yes.
usually denoted by beta, and usually considered -2 for low massive galaxies, right? Or
Uh,
high masses.
the phenomena of the beta is different. Beta
Uh-huh.
is the UV slope.
Okay. Yeah. Yeah. Yeah.
However, this is just a ratio.
Okay, 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 okay. Very good. So these people, the new paper which you're talking about, which makes use of JWST data, like they
Yes.
look into like I think three or so. Yeah.
Three galaxies they have observed.
How many?
Three galaxies
Three
at the
galaxies.
redshift of 7.8
Yeah.
with the masses of exponent 8.
Uh, okay. So they are looking at very high redshift galaxies.
High redshift.
Yeah. Very well. So this is with the UV part. On the IR part, we also had another paper where we talked about the dust temperature particularly. So IR, when we talk about IR, it's usually the heat or the temperature part. So here you, in this paper, I think you have made it very clear, which I think also the previous authors uh,
Yeah.
also discussed different kinds of temperature, and you were very particular on defining all these clearly. And the most important part here was our finding that how CMB, which is the background cosmic radiation we have, impacts the temperature of dust, right? So this is, I think, very interesting output of this work. Can you explain a little more about what's going on here?
Yeah. So Prajwal, what is happening in the local universe? The CMB temperature is very low. It is about 2.7 Kelvin.
So today it's very cold. Yeah.
It is very cold, yeah. So with this temperature, it highly affects the dust
Yeah.
around it.
Yeah.
So, but this is not the same scenario when we are talking about the high redshifts.
Yeah.
In the early universe, the temperature of the CMB was higher.
Yeah.
Yeah. So in the redshift of 8, it was about 24 Kelvin,
Yeah.
and then it decreased to the 22 Kelvin at the redshift of 6.
Yeah.
So still this temperature is too high as compared to the dust temperature.
So let's
That's
put into picture, like maybe dust temperature was around 18K or something,
yes,
18 Kelvin. Yeah.
even lesser. It
Yeah.
depends on the location of the dust cloud
Yeah.
and the
Yeah. Yeah.
location of the stars.
Yeah. Yeah.
So even we can clearly see in the third panel,
Yeah.
where if we do not include the CMB radiations, we can see
Yeah.
the dust temperature is actually decreasing.
Yeah.
So at the very center, the dust temperature is very high, which is about 35 Kelvin, and then
Okay.
it is decreasing
Yeah.
when we are moving far.
Yeah.
So, and it decreased to the 10 Kelvin or even lesser.
You're
But
talking about this one, right?
the
The,
third panel,
this one.
uh, in the image, this is the second panel, but in the full figure, it is the third panel.
Ah,
The
yeah, got it. Well, this is the first one where
yes,
we plot actually the stars in the galaxy, right? So
star particles, not
yeah,
yes.
yeah. So every point here is a star in this.
Star particles.
Yeah, star particles. Uh,
Yeah, because the star is like a individual star, but
yeah,
a star particle is a group of the stars which
yeah,
are having the same properties.
yeah. Well, we have to be very precise in astrophysics because we call them star particles. Well, because the simulations are big. So when okay, so the third part is where we do not have any CMB, where all the heating is coming from the stars, correct?
Yes, yes,
So here we see that only at the where the stars are present, you get a very heated environment.
yes.
There is no and the edges of the galaxy are less
Are
heat.
very cold.
Yeah. So how things change when we include CMB? So the
So
CMB
CMB
tries
is
to
actually coming from the external environment.
very nice.
So from outside of the galaxy, when it is coming inward, so
Yeah.
the highest temperature that hits is at the edges of the galaxies.
Yeah.
So and then it again decreasing
Yeah.
due to the shielding effect.
Yeah.
So here in the last panel, what we are seeing in any of the figure, so the temperature is way too high because it is in the log scale. So we are just seeing 1.6. However, we convert it is a little higher temperature,
Yeah.
about 25, 26
Mm,
Kelvin.
mm,
Yeah.
mm.
And then when the CMB is coming inward, it is decreasing.
Yeah.
From the outside, the dust temperature is higher
Yeah.
and then it is decreasing.
Yeah.
So the decreasing is because of the dust shielding effect.
Yeah.
Dust is also trying to stop penetrating the light.
Mm.
So here is the phenomena. That's why we are still seeing some dark patches in the galaxy images.
Yeah.
These dark patches is the very high density where the new stars could be found.
Yeah. You call it clumpy regions or something.
Yes.
Yeah. So yeah. So this is, I think, one of the very interesting output here. And going back to our paper here, and I think we also study the another interesting aspect, which is the beta versus IRX, right? So
Yes. So when
why
it
is
comes
it
to
important? How to think about it, and how is it related to the star formation rate?
yeah, so let's first say what is the beta UV. Beta UV is just a slope.
Mm-hmm.
Yeah, the slope of the UV light. So if we see that how the spectrum of the galaxy look like, so it is
I'll share it again for now. Okay. Yeah, you can go on.
okay. This is the wavelength, and here we can see the spectrum SGD. So in the log scale, what we are seeing, this is how it's supposed to be like.
Mm-hmm.
So this is the spectrum of any galaxy.
Mm-hmm.
Let's assume that star is very hot.
Mm-hmm.
So if it is hot, so there is a high chances it is emitting the shorter wavelength.
Mm-hmm.
So the LCD will move toward here.
Mm-hmm.
And if the star is less hot, then it emits in the longer wavelength.
Mm-hmm.
So here the beta slope is actually the ratio in the region of the UV light. So if the ratio is positive, if the slope is positive, we consider it are massive galaxies with a higher metallicity.
Mm-hmm.
But if the slope is getting negative, it is more UV light emitters and the low metallicity
Mm-hmm.
stars.
Mm-hmm.
So this is actually the basic idea about the UV slope.
Mm-hmm.
However, IRX is also a ratio between the IR luminosity and
And the UV.
and the UV.
Yeah.
So we are saying the points we are getting is a very negative. Very negative means that the galaxies are having a very low metallicity and the stars within it are very young.
Mm-hmm.
And the other point we have highlighted is that the stars, the galaxies at the redshift of 8 is having a higher IR emission
Yeah.
as compared to the galaxies at the redshift of 6.
Yeah.
This higher, uh, this difference is coming from the CMB because
Yeah.
at
Yeah.
higher redshift, the CMB was stronger. It heat the dust
Mm.
even more, and that's why the temperature and the re-emission is higher
Yeah.
as compared to the redshift of 6.
Yeah. As you can see, like the SMC model is completely out of sync for high redshift galaxies, right?
Yes, this
The
is true.
calcity is actually showing the trend, but even if you go to very high redshifts, even calcity is slightly, I mean, are
So yes, so previously what is wrong with the previous models? They get all collapse with a very low IRX values
yeah.
because they were not in the simulation. They have not included the CMB as an external influenced.
Mm.
So while removing the CMB, what happened? All the stars, even all the points we are seeing in here, get all moved toward down if we
Yeah.
just remove the CMB. So
Mm.
CMB has the power to increase the IR emission. So these are the models that were like, this is the model which were not involved initially
Mm.
in the previous simulations.
Mm.
And yes,
So these points which you have marked in black are the real observations.
yes,
Yeah, these are real galaxies. Okay, very well. I mean, this is a paper before JWST, to be sure. All
yes,
right. It would be nice to plot this again with the new observations. Yeah. And coming back to this plot, I think this plot is missing one of the things, right? Which is the usually the attenuation curves will have this bump, which is
yeah,
primarily because of some element.
we get a bump at 2175
Exactly.
angstrom.
Yeah.
Yeah, so that bump is because of the graphite component. Yeah,
Yeah.
but in the high redshift, we do not observe or we do not have the graphite elements.
Yeah.
That's why it does not impact our results, and we are even not seeing it in the observations.
Well, so do you think, do you want to, is there any other particular things you want to discuss? Any particular output or result which you
Yeah, Prajwal, if you go into the same paper
yeah,
at the plot of attenuation,
yeah, yeah.
attenuation versus the masses.
Ah, attenuation versus the mass. Where do we have? Yeah,
So this is kind of very much interesting. Yeah, it
yeah.
always fascinate me while every time I see this. Yeah,
Hmm.
because here we are saying that at the lower stellar mass galaxies, the attenuation is almost zero. It
Yeah,
means that all the light can easily escape
right.
without any absorption.
Yeah,
However, the dust still emits the IR radiation,
yeah,
and that IR radiation emits because of the CMB.
yeah,
Yeah. So
yeah.
mainly we can see that if it is emitted because of the CMB
Heating due
release.
to CMB. Yeah.
Yes.
Very well.
So now we are saying that if the stellar mass is increasing, the attenuation is also increasing, like the more absorption of the light is happening. But it is not the same phenomena for all the galaxies. So we have witnessed some of the galaxies where even with the higher masses, the attenuation is lower. Yeah, so that is actually a very interesting point, like why it happens. Like
Mm-hmm.
even the mass, if the mass of the galaxy is higher, it means it consists of a more dust in it.
Mm-hmm.
More dust means more attenuation.
Yeah.
Yeah, but it is not happening.
Mm-hmm.
So while performing the simulation at each redshift, at each interval of redshift from 10 to 6, we have witnessed that there are some phases when the galaxy showing a very high attenuation,
Mm-hmm.
but then the attenuation decreases.
Yeah.
That decrease is could be due to the very strong feedback mechanism.
Mm-hmm.
So the feedback mechanism is the either the supernova feedback or the AGN feedback, where the power, the energy released by these phenomena
Mm-hmm.
are so high that it dislocate the dust positions.
Mm-hmm.
So, and it clears the path for the light to easily escape from the galaxies. So
Yeah.
that's the reason the attenuation curve decreases. So roughly, if we see it,
Is it also the case where dust grains also get dissociated in a sense that UV will
uh,
break the dust grain?
unfortunately, I cannot pass any comment on it
Yeah.
because it is hard to say that the dust grain itself dislocated or dissolved,
Mm-hmm.
because the observation is saying that the dust cloud itself get dislocated, like move from one place to the
Ah.
other place because of the high energy emission. So
Mm-hmm.
it clears the upcoming light to easily escape from a galaxy.
Mm-hmm.
So what we have seen is that this is a redshift and this is the attenuation. So we
Mm-hmm.
have seen that I at high redshift, and this is from 10 to 6, we have seen the galaxies evolve, the attenuation in the galaxies evolving
Yeah.
from 0 to the higher values,
Yeah.
and then all of a sudden it get collapsed
Mm.
for a certain period of time,
Yeah.
and again it increases.
Yeah.
So
It is
this
interesting.
phenomena, we have seen that why, what is just happening.
Yeah.
So we have seen that it is due to the strong feedback effects.
Yeah. So Muzammil, you are.
However, for the other galaxies, it is not always the case. For other galaxies, the phenomena is very much clear that it always increases.
Yeah.
And then
Yeah, I remember you talking. This could be also because maybe there were some merger events and the dust clouds maybe dislocated from due to gravitational, effects.
the other possibility is the galaxies merger, but
Hmm.
the chances for the galaxies merger is quite low, because
Yeah,
the galaxy, if these are the galaxies merging phenomena, then the amount of the dust actually increase
yeah,
instead of the decrease. So
mm,
if the dust is increased, then the attenuation must be way too high.
yeah, yeah,
But I think that it is not the case. It is the pure case of feedback.
yeah. So we have discussed quite a lot today, particularly focusing on early galaxies. Uh, so you have been doing simulations, like I just as a side note, like I've seen you run these big simulations for months together. It take
Correct.
even utilizing the computational facilities provided by University of Heidelberg, ISW. But still, these big simulations take a lot of time and a lot of patience. and any sort of mistakes will cost you lost a lot of months. So tell us about like what are the difficulties you faced in doing such works related to simulations?
The simulations like the radiative transfers are always very heavy simulations. For me, in total, it took 7 months
Hmm.
for 100 galaxies to simulate.
Yeah.
So this is actually a very huge time frame, especially for the master students. So we can rethink it in the different ways, like how can we reduce the simulation time?
Yeah.
For example, a galaxy, if a galaxy consists of 100,000 stars,
Mhm.
and we simulate each and every star particles, yeah, so it is going to be a way too lengthy simulation. So what is the other alternative? So we came up to the point that just reduce the number of particles.
Yeah.
So just randomly take only 10,000 star
Yeah.
particles, but then it will definitely it is going to affect the whole other things.
Yeah.
But if we are decreasing the number of star particles but increase its luminosities,
Mm.
so the final effect will remain the
Yeah.
same. So these are the strategies we need to take while doing the simulations.
Yeah, this is what I really enjoyed working with you, is that how innovatively you came up with these alternative solutions. Like, of course, it is taking long time. Then how do we cut short it? Like, you take some shortcuts, but we have to also keep in mind that this has to be realistic assumptions. So if you are
Ye-
reducing number of star particles, you have to somehow make it up for it, like, right? So
yeah,
you
because
increase the luminosity.
when we are seeing our simulation, so the all the star particles are accumulated in the region of 5 parsecs,
Yeah.
5 kiloparsecs. However, the halo, the image of the halo we have is about 25 kiloparsec radius. It is too much. It
Yeah.
is way too bigger as compared to the region of the star particles.
Yeah.
So if we are doing some assumptions on the
Yeah.
smaller scales, so
Yeah.
it will not eventually affect the whole simulations,
Yeah.
and the result is approximately the same.
Yeah. And so now also asking another slightly deviated topic, like, okay, so now you've done some extensive work on like very involved works on these highly reputed simulations actually, and they have been all also been cited very well. It is being received very well, and you published this in one of the very good journals, which is monthly. Uh, uh, what is that?
Royal Astronomy
Yeah,
Society.
monthly notices of Royal Astronomical Society, which is very high. I mean, for astrophysics, I think
Very
one of the
high
good,
impact journal.
yeah, journals. And even our own idol, who is Desika Narayan, who has done a lot of work on dust attenuation, cited our
Like
paper.
I have learned a lot from him, from his papers, and amazingly he acknowledged us in his
Yeah,
paper.
man. It's a very big full circle, I would say. Like they citing our paper is a big reward, I would say. Uh, I think so. I think what comes to my mind is like I think why it always surprises me that uh, why you chose industrial sector having all these achievements. Like I think you have several, these are only two papers, being as a master student itself is a big deal, but you also have other papers coming from your undergrads as well, but you still chose slightly on a industrial part. I mean, of course you still have this interest to learn about universe, do more projects on it, but however you're now slightly deviated towards uh, industrial data science. I think you're nowadays involved with more fancy sounding stuff, deep learning, AI, all these things. So what is this detour? What is this deviation about?
Prajwal, I say that we always need to remember why we have started something, yeah?
Yeah.
Because my keen passion and my keen interest was to know how these things ever work, like the universe. how the galaxies evolve and form, and what are the mechanism inside of it. So I was always interested to know about these things. When I work on it, so I learn a lot. We publish the papers. Everything is good. But one thing I feel bad about it is that uh, the acknowledgement that we should receive from our work is very less,
Mm-hmm.
especially from the academic side.
Mm-hmm.
So this was like a turnover for me.
Mm.
So I was like, at that moment, I just decided that academia is going to be a little toxic for me.
Mm.
So I just deviate my path from
Yeah.
it.
But we are still working on few things which
Yes, because I like this field. I
yeah,
like to do research in astrophysics,
yeah,
and I will always ready to collaborate on it.
yeah. Well, on that note, it was a pleasure talking to you today on various things. And I'm really happy that we were able to collaborate on this, even though my contribution to this work is, as I said, very insignificant. And all the credit, if these two papers should go to you. And I'm really happy how it is being received these days in the
Prajwal,
light of JWST.
Prajwal, I must say that it is not always the case. Not a single person is capable to publish anything. Yeah, like
Yeah.
it is always a group. Yeah. So in my group, if I am saying that my professor, my supervisor, all are in group, the same as you were in the group. Yeah. So you help me, you clear my doubts. We have worked on it, and yes,
Yeah, so I mean, it's really nice to see how it is being received in the recent days. And well, we'll try to publish. I think not, it's public. See, the motivation is not publication, but anyway, we have some really amazing project going on right now, which is about where we are looking at black holes now. And uh, we'll talk about it in the next podcast, maybe. But very happy to collaborate with you and see you grow in other sector now in deep learning and AI. And I wish you the very best for whatever you do, man. I'm sure you'll do great. And see you again next time. Yeah. Have a nice time.
thank you, Prajwal.
Thank you.
Bye.